Now let's talk about short truth tables. First of all, look at this example of an invalid argument, which we did in the previous tutorial. The truth table has 8 rows, but actually we're only interested in a subset of those rows. Which ones? We're interested in finding rows in which the premises are true and the conclusion is false, because that's the test for validity. So if we're only interested in those rows, what about all the rest of this work that we do? It's basically work to complete a truth table that we're not interested in. And so we could actually focus more on the goal of identifying the particular rows that we are interested in using a kind of shortcut technique. So that's what I'd like to show you now. So we're going to use the same argument. P and Q implies RP, therefore R. Only instead of constructing the entire, so P and Q implies R, P, therefore R. Instead of constructing the entire truth table, we're going to start at the opposite end. So we know from the previous example that this argument is invalid, but if you didn't know that already, you would construct the truth table in exactly the same way. So here's how it operates. Assume that the argument is invalid. If the argument is invalid, then what happens in terms of the overall values of the expressions that compose that argument? Well, if the argument's invalid, then the two premises are going to be true, and the conclusion is going to be false. So that assumption, assuming that the argument is invalid, is the starting point for the short truth table method. So what we'll do now is, based on this assumption, and you need to bear in mind that it's always an assumption until we find a row that makes it true. So start with the assumption that the argument is invalid, assign true to the two premises and false to the conclusion, and then above the variables we're going to write ourselves some notes that will help us find the row. So if this conclusion is going to turn out to be false, what does R have to be? Obviously, R has to be false. So we're going to make a little note that it's false and circle it. Circling it is a way that I have to remind myself that this value for R cannot be different. In other words, there's no other value we could assign to R that would make the conclusion false. So R has to be false, in other words. All right. Same with P. Look at this premise. If this premise is true, which is our assumption, then the only value P could take is true. So we'll put P as true, and we'll circle it to indicate that it can't be otherwise. Now, let's look at the other instances of R. If R is false here, then it has to be false here. And because it can't be otherwise, we'll circle it. And if P is true here, then P has to be true everywhere. So we'll make a little note that P is true and circle it to indicate that it cannot be otherwise. Now let's look at this particular situation here. Okay, what would Q have to be to make this expression turn out true, given the fact that R has to be false and P has to be true? Well, think about it. Q can either be true or false. If Q is true, then true and true is going to make true for this expression and false for this expression, right? Because R has to be the same, and true implies false is false. But that conflicts with what our assumption is, so Q cannot be true if our assumption is going to work out for us. So the other possibility is that Q has to be false. So if Q is false, what happens? True and false make false, and false implies false is true, which is exactly what our assumption is. So that means that the value we're looking for Q is false. So what does that tell you? It tells you that there is one row, at least one row in the truth table, and that row is going to look something like this. So you've got P, Q, and R, and there's some values here, and some values here, and some values here. But there's one row where P is true. That's what we learned here and here. Where R is false, that's what we learned here. And, of course, the value that we used for R in the premise is false. And Q is false, whatever else. So whatever else the truth table has in it, it's got this row in it. And this row is what makes this assumption turn out to be true. Now, if you assume that the argument is invalid and you can find a row like we found here that makes that assumption true, then you have just proved that the argument is invalid. And in fact, what we've actually done, look at the values here, true, false, false. If we go back to the full truth table for this very same argument, what we see here is that we found exactly the same row that we were looking for, a row where P is true, Q is false, and R is false. Only the way we did it here was to construct the entire truth table, which involved extra work that we don't even care about. For instance, these rows where R is true don't tell us anything useful at all. So any row like that is automatically wasted effort, right? So going back to our short version of this, to the short truth table approach, since we started with the assumption that the argument is invalid and worked back to find values that would make it true, we've done exactly the same job, which is proving that there is at least one row in the truth table, meaning there's at least one set of values for P, Q, and R that make the premises true and the conclusion false, which violates the definition of validity, which means this argument is invalid.